Okay, it seems to be working. That's good. Let's hope it doesn't explode again. Oh my goodness. Okay. Alrighty. So we have more thermochemistry to talk about today. We may or may not finish all of it, but if not, that's what Monday's for. So, okay. So just so you know, I did put homework up yesterday, so you have plenty of stuff to do. Again, that's due next Sunday, so not this Sunday, but it's whatever, October 4th or something, whatever that Sunday is. So that's when that will be due. But of course, I do suggest you start on it sooner, because the sooner you do it, the sooner stuff will stick in your brain. So last time we did kind of constant pressure. What was called calorimetry. And from that, we were able to see that the enthalpy for our reaction was equal to the heat at constant pressure. So exciting stuff. You'll often see this stuff called a coffee cup calorimeter, because what that looks like Look at how good I am at drawing, everyone. Woo. That's a thermometer. Okay, because these experiments are typically done in styrofoam coffee cups. They basically are there just to insulate against heat loss. And so you do this, and you can measure the temperature change doing this. And we saw that we had a formula that would tell us the heat that's happening in there. And we also saw that the heat of the solution was the opposite of the heat of our reaction. And so this was done at constant pressure, because these things are open to the air. So that's the same pressure, essentially just atmospheric pressure helping out there. So there's no work being done. So all of the energy change is related to heat. Cool. So this is kind of a rudimentary way to do some thermochemical calculations or experiments, which is something that we typically do in lab. So once I get around to finally getting lab stuff for you guys, there will be certainly an experiment like this, where we're doing some calculations related to this stuff. So we also have a different type, which is going to be constant volume calorimetry. By the way, calorimetry means like basically heat measuring. Just because we have another unit of heat called the calorie. Just so you know, a calorie is equal to the specific heat capacity of water in joules. Just so we know. It's a thing. I would not expect you to memorize this number, but there it is. And just so you know, 1 calorie with a capital C, because why not, is actually 1,000 calories. So if you look on your bottle of sriracha or whatever you happen to have that you're looking at nutrition facts, you'll see calories with a capital C. That means 1,000 calories. So, oh, what do you know? This sriracha apparently has no calories in it. So rounding things that have happened there, but go figure. So those calories that you see on your nutrition labels are actually kilocalories. So they're 1,000 of regular calories. So yeah, just so you know. Cool. So with constant volume calorimetry, we have what is called a bomb. So you may also see this as called bomb calorimetry. And that just means it can withstand high pressures. But again, since we're going to have constant volume, this is a very rigid container. Rigid. Let's try that again. Rigid. That means that the change in volume is 0. So we have constant volume. So again, no work is being done here. Correct. So the 2,000 calories that you eat per day, or whatever your daily calories are, that's equal to, chemically speaking, 2 million calories. And that would be enough energy to raise the temperature of 2 million grams of water by 1 degree Celsius. So, just fun facts. Okay, so in this bomb, of course, we'll have our thermometer. We'll have like a reaction chamber that's in there. We'll have some like vents and stuff. This is where like most of the like calorimetry stuff is done for fancier people doing calculations. And usually there's water around this to absorb the heat, which we can then measure with our thermometer. And the reaction goes in here. These are so specifically designed that very often you will calculate the specific heat of the calorimeter is going to be established by some procedure. So you're either going to burn something that you know how much energy it produces, and you will be able to see how much heat capacity your calorimeter has. And so this makes calculations pretty easy for us. We're going to see that the heat of a reaction is just going to be the change in temperature times the heat capacity of the calorimeter. So the calorimeter is done just as one unit, so there's no mass associated with this necessarily. And so just so we know, again, this is essentially this is Q solution for a constant pressure system, but this one actually takes into consideration the entire device. So it just makes it easier. So we don't have to worry about masses of solution and all that stuff. The mass is always the same for the calorimeter because you use the same calorimeter every time. And so therefore, we no calorimeter mass is needed. And so you'll see you have a couple of problems in your homework about using constant volume calorimetry or bomb calorimetry. And so all you need to know is the specific heat, or rather the heat capacity of your calorimeter and the change in temperature. That's it. So let's go ahead and see what this looks like. And very often the reactions that you're doing in these are combustion reactions, because that's a very easy way for us to establish how much heat is released. It's kind of just a standard practice. Yeah, we can do this. Let's burn some propane. We can do that. And suppose, for this one I'm going to make it up, but for the rest of the stuff today we're going to see I have to use book stuff because the numbers are very specific and I do not want to confuse you. So for this one I can just make stuff up. And let's say that the specific heat of the calorimeter, sorry, I keep saying specific heat, I mean heat capacity, is, let's say it's, is that an appropriate number? Probably not, but whatever. I'll pretend it is. And let's say the temperature goes from 21 degrees Celsius. That's pretty much room temperature to, I don't know, 24.2 degrees Celsius. And so we can calculate delta H for this. So just like before where we had for the constant pressure one, guess what? For here, the enthalpy will be just related to the constant volume Q. Okay, but remember that delta H for a reaction is going to be related to the moles. So again, we usually report delta H for a reaction with respect to moles. Delta H for just a process is related to just how much you're burning or reacting or whatever. So with this being said, we can use these two guys to calculate our Q. So Q for a constant volume, remember, is just going to be negative of your calorimeter multiplied by delta T. So we can just plug in our numbers. Again, I'm kind of making up that number. I honestly have never used a bomb calorimeter, so I have no idea if that's an appropriate number or not, but who cares? Again, we always do final minus initial. So that's going to be 3.2. And so 7.812 times 3.2. Oops. And for this we get apparently negative 24.9984 kilojoules. Oh, I'm sorry, this is kilojoules per degree Celsius. I apologize. Remember, heat capacity is per temperature, right? Great. Perfect, Tyler. So that's great. So it looks like we are going to have two sig figs for this. So we know that delta H for this, for the 1 gram, was equal to negative 24.9984 kilojoules. So if we want to find out what it is for the reaction, we can do that as well. I guess we should actually, yeah, that's fine. For 1 mole, we can figure that out, right? So we have, we want to find an answer in kilojoules, right? We have grams of our substance. We now have, oops. We can find the molar mass, right, of propane, and from that we can find our moles. And remembering that delta H reaction is going to be the Q divided by your moles, we can figure out what this is going to be, right? So who's got our molar mass of propane? Let's see. Propane. $44. I have a slightly different one. Yours is just fine, Tyler. And I guess Kevin's is also slightly different from mine, but whatever, it'll all be okay. So doing this, 1 divided by 44.097. Again, our numbers are so small in difference, it's not going to make a problem when doing a multiple choice exam, because I'm not going to give you very, very similar answers, right? So 22677 moles. This will need 3 sig figs, so delta H for our reaction will be equal to negative 24.9984 kilojoules over the number of moles that we had. Okay, so 24.9984 divided by 0.022677. Doing all this fun work. Yeah, that's okay. That's fine, Tyler. It'll all work out. And so it looks like with all this stuff, we have 2 sig figs versus 3 sig figs. So technically, we would round that to 1100 kilojoules per mole. Oh, you're absolutely right. It should be negative. Why is it negative? Or rather, what does that tell us? Yeah, it's exothermic. Just double check your calculation, Starlord. Because we have like a number divided by a really small number, so we should get a big number. So just double check, recalculate it, and try that again. Yeah, and so of course exothermic, right? And we already know that combustion reactions are exothermic, right? Where they release heat. Okay, so it's a little bit easier. We just don't have a mass term to deal with. So at least for the calorimeter. So fun. All right, do we have any questions on this one? And Starlord, let me know if you calculate it again that you get the right or the same answer as the rest of us. Not the rest of us, only Kevin and I apparently have this answer, so both of us, I guess. Where's my coffee? Yeah, here. I would ask you specifically, Shane. For example, let's go to your homework. Let's see. Let's see. Okay, so I don't remember if I gave you number 41 or not, but 41 reads, blah, 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 part A. What is the enthalpy change for this reaction per mole of O3? When you see enthalpy change per mole for the reaction, that's delta H reaction. If it's just delta H, and it's just like there's just a number, and there's no reaction given, that's just a regular delta H. But if you ever see something like, well, this one gives us an actual equation, right? So 203 turns into 302, and it says delta H equals negative 284.6 kilojoules. This is a delta H for the reaction. Okay, good. Well, there we go. So it's actually a very good question, Shane. I had not, yeah, it was Shane, that I had not thought about. This here is our delta H reaction. And remember that delta H reaction will always go with coefficients, right? So this tells us 2 mole of ozone equals this thing, or 3 moles of oxygen will equal the same thing. So that's what we mean by delta H reaction. So either it's going to be written on the side of the reaction, and so that's what that tells you, those conversion factors, or it will just be asked, what's the enthalpy for the reaction per mole of whatever, and so that's what you'll get. Okay, so that's how you're going to know for that. Because enthalpy is what's considered an extensive property, it depends on the amount you're using. So the delta H that we just had up here, that was equal to QV, that was our just like enthalpy for this 1 gram. But if we want to do it for the reaction, that's when we have to use the moles. So hopefully that makes sense. Most often you'll be calculating delta H reaction, because that's the stuff that we'll actually be using in calculations. It's just experimentally you'll get regular enthalpy. Very exciting. Well, perhaps we'll just let that sink in, and we'll go there. Okay. So Shane, hopefully that will at some point click. If not, we can discuss it later. Okay. So we are going to move on to a new section, which will be on what is called Hess's Law. And that's just going to say, because this guy is a state function, if a reaction is done in multiple steps, delta H, or the sum of the delta H's, will be equal to delta H for the 1-step reaction. What the heck does that mean? Let's find out. So for example, okay, this is where I'm going to have to use our book, because I cannot make these numbers up. I think we use carbon dioxide for this one. Yes. So we have combustion of methane turning into carbon dioxide and water, right? So this is we're going to see that states of matter are going to be important here. And so this could be a particular reaction. Yes, we've seen this reaction before. And delta H for this reaction is, where are we? Here it is. Negative 890 kilojoules for our reaction. It turns out that while we could do this in 1 step, sometimes what happens is we could have it happening like this. And I understand you guys are going to say, well, what the hell, who cares? We'll see. So often what you'll see is, of course, when you're burning stuff, you don't see liquid water forming, right? That's just pretty normal. However, we do know that water is going to be a liquid at normal conditions. That is to say, like room temperature and normal pressure. And so we also know we could have a reaction that tells us, okay, that we can have water condensing into a liquid. And so we're going to see that this process, okay, I shouldn't make these numbers up. Oh, thank goodness I didn't. Okay. The delta H for these two reactions are given. Let's look what happens when we add these reactions together. So we can totally add reactions, totally normal. If we do that, so I'm just going to keep all of our reactants together. What was I doing? Water. Okay. Technically, are we gonna have to double this because this one probably has two already. Oh, no wonder. Okay, my apologies. It's so hard to keep these together. Yeah. We're gonna see they equal each other, right? And so that means that delta H, the total one, is delta H for reaction 1 plus delta H for reaction 2. And so we should see that negative 890 kilojoules equals negative 88 kilojoules plus negative 802 kilojoules. Hooray, it works. And notice that just like in any other mathematical equation, if we have the same thing on both sides, we can cancel it out. So by combining these two reactions, we're able to talk about both processes. So first the regular combustion, and then the second one, the water condensing into liquid. We have reactions for both of those. And we see that now what's left is that same reaction we had that was just one step, where the water is already liquid coming out. And again, you might be like, well, what's the point? We're going to see that we're going to be able to calculate delta H for a reaction without having to do any combustion. Just by having other reactions that we do have delta H's of, we can figure out the delta H for a particular reaction. And so it's just going to save us a ton of time and money. We're not going to actually have to do the experiment itself. And so let's see this in another scenario. Okay, here we go. Let's see, what examples do we have in our book here? Okay. So, another example, this is going to be example 5.9 from our book, which is going to be we're going to try and burn some carbon. Exciting stuff, yes? Okay, and so we're going to see that the enthalpy for this reaction is negative 393.5. All right, however, in real life, it is very hard for us to actually do this reaction because, these are always going to be written in their normal states. That is to say, there are states at 25 Celsius and 1 atmosphere. Very good point. What we're going to see here is sometimes, in reality, we actually have two reactions that are going to be taking place here. We have carbon monoxide that could be formed, and we could have carbon monoxide that is turning into carbon dioxide. And so let me find the delta H's for these guys. Oh, I'm sorry. Oh, whatever. I lied to you. That's not what we're solving. Oh, I'm sorry. I hate having to do this out of the book, but these ones you just cannot make up. This is actually the one we're trying to find here. And so with this one, we have calculated it to be negative 283. And so, given all this information, we can find out what the delta H for that second reaction is going to be. So we're able to burn carbon to make carbon dioxide. We're able to burn carbon monoxide to make carbon dioxide, but it's very hard for us to kind of stop at carbon monoxide. That's what I had meant to say. And so from this, we can actually figure it out by using Hess's law rather than actually trying to do this experiment, because it's just not going to happen. It's very difficult to stop this reaction at CO. Normally, it's just going to keep going straight away. One thing to notice that you'll see is we have these pesky fractions in our thing. Typically, we have the coefficient of the product is 1. So to do that, we might have so it'll be okay to have fractions of these. You'll see them quite often. And so you're going to see that I posted for you guys on Discord. Actually, I have it here on this computer. Let's go to our extra resources. Okay, so we're going to see here that I have given you a website that has what are going to be thermodynamic values for different substances. We're only going to be focused on this column. But all of these reactions, all of these numbers that you see here, are for formation of 1 mole of that substance. And so sometimes we're going to see that we may have to have pesky fractions in our things. So we're going to explain how to use this a little bit later. Right now we're just going to focus on individual reactions rather than heats of formation. I would not do that. The reason for that is it's going to make your life a little bit harder. If you do it, Melissa, it would work. I'm going to do it in red. For example, that last one, that last reaction there, I'm just going to duplicate everything. We're going to see that delta H for this will be negative, I'm going to have to calculate, 283 times 2. And that's going to be 566. And so we're going to see it's just going to make our lives more complicated because I don't know why I wrote that. I'm going to have to rewrite everything here. We know that this is kind of the total reaction up here. We're going to see that if we try and add these reactions together, these other two ones down here, if we try to add these together with having these pesky coefficients, that's just going to make our lives harder. And so we don't want to have to worry about doing that. So typically you will want to make sure your coefficient for your product is 1. And so you may have to have fractions for your reactants. Again, this is just kind of something unique to thermochemistry. It's not how we talk about chemical reactions and pretty much anything else. It's pretty much only for thermochemistry, maybe sometimes for electrochemistry as well. But mostly this is how it's going to work. So I'm just going to go ahead and label this reaction 1 and reaction 2. And we have our total reaction there up at the top. And so we know our total reaction is going to be reaction 1 plus reaction 2. And so the delta H for the total reaction is going to be equal to the sum of the two enthalpies. Yeah, and so Shane, you're absolutely right. This is easier than it seems. We see 1,000 reactions with all these horrible fractions, but yeah, all we have is simple math. So we have here that our total reaction is given to us as negative 383 kilojoules. We're trying to find delta H for reaction 1. And we are given delta H for reaction 2, which is negative 283. I'm sorry, it was 393.5. Wow, I'm really bad at copying numbers, it seems. And so as Shane has calculated it for us, we have negative 110.5. Yeah, exactly. Kilojoules equals delta H 1. Yeah, this is not tough. And actually, so notice this number that we've calculated. So that's carbon monoxide. We can actually kind of double check if we go to that lovely gigantic table that I've given you. We can find carbon monoxide, and lo and behold, we can double check, oh, that is actually our answer. So bunch of scientists, way back when, have calculated all this stuff. So these are already established values. So you can always kind of double check your work here. So the delta H for kind of making carbon monoxide is already established as negative 110.5 kilojoules. And lo and behold, here in this mathematics using Hess's Law, we have calculated it doing this instead of having to do an actual experiment. So we're going to see the only things that are tricky here is sometimes we will have to reverse reactions. And we'll do an example of that. So one thing to note, delta H, if we are to reverse a reaction, the delta H just becomes the opposite. Because these are state functions again, it doesn't really matter what the process is or anything like that. If we instead had the opposite reaction, so we had C plus O2 turns into CO2, solid, gas, gas. We saw that the delta H was negative 393.5 kilojoules. If we have the opposite reaction, the delta H for that is going to just be the same number, but positive. So if we ever have to flip a reaction around, just understand you just change the sign of delta H. That's it. Nothing too crazy there. If you ever have to multiply a reaction by a coefficient to make your stuff work out, you would just multiply delta H as well. So delta H would just be, I don't know, 787 kilojoules. It's just twice of the, you just multiply delta H by 2 also. Okay, so, yeah, that's easy. Okay, let's do some more examples. Okay, here we go. Okay, here's one for us. Again, because these values are already like written, I want you to be able to check your answers, so I can't give you fake numbers. That's the reason that I can't do that. So, here's a problem. It is number 5.10 in our book. It's asking us to calculate delta H reaction for, is it 2 carbons? Yeah. Is it C2H2? Yes, it is. Okay. So it's asking us to do this, and it's giving us 3 reactions. Okay. Thermochemistry is awful, we all know it. So it's giving us the 3 reactions here. And I know this, you guys are saying, like, what the hell, half of this stuff is not even in this reaction. That means it's going to have to cancel out, right? So we're going to see how this works. And delta H for this guy is negative 1299.6. We have another reaction. Okay, I'm going to spread these out a little bit. Oops. Carbon plus oxygen turns into CO2. We just saw that one was negative 393, right? And then the last one we have is combustion of oxygen. So remember, most of these are combustion reactions. That's what we have done in our bomb calorimeters. And so that's why, even though this top reaction is not a combustion reaction, we're going to be using combustion reactions to calculate it. Oh, and then delta H is going to be negative 285.8. All these are kilojoules, of course. Okay, so with that, we know we're going to need to have this acetylene molecule, C2H2. This is going to be a product, right? And these two guys are reactants. And so we need to make sure that in our kind of reactions here that we're going to be combining together, that the products will be on the product side and the reactants will be on the reactant side. So if we look at that first reaction that's given to us, we see that acetylene, which is C2H2, is on the left side. That's a reactant. So this one we will need to reverse. Do we all see that? Because in the reaction that we're given for the combustion, it is on the left side. So we have to reverse it so that it will be on the product side. Okay? For the second one, we see carbon plus oxygen turns into CO2. However, if we look at our reaction that we're looking for, we actually need 2 carbons, right? So if we're going to make this all work out, we're going to have to double this one. So that way we end up with 2 carbons in our reactant side. And finally, we have hydrogen burning. That one looks okay, right? It already has H2 as a reactant. We're okay. So we're going to leave this reaction alone. So let's go ahead and now do all this stuff. So let's reverse that first reaction. So if we reverse it, delta H will become the opposite side. So now we have a positive delta H there. To double the second one, we're going to just have to multiply that by 2, which was, oh, I had already calculated this. What was it? 787. 0.0, I guess. And the last one we're just going to leave alone. So, by doing this, we should see that the stuff we do not want should cancel out. So, we remember that we want this is the reaction that we want. So let's just double check that everything that we do not want should cancel out. So very first thing in our reaction is 2 carbon dioxides. We do not want those. So let's make sure they cancel out. And indeed, we see we have 2 carbon dioxides that we can get rid of. So we're going to be combining all the reactants and all the products. If the same thing is on both sides of the reaction, get rid of it. Let's check water liquid. And indeed, look, lo and behold, we have water liquid on both sides. Get rid of that. The last thing we don't want is 5/2 oxygen. And if we look, these two guys together are 5/2 oxygen. Go away. That'll cancel out. So notice we are left with now 2 carbons, hydrogen gas, producing acetylene. And so that means now that we have made sure that everything is in the right direction and the right coefficients and everything, we can now do the adding up. So the delta H for the total is going to now be the sum of these 3 reactions. And thankfully Kevin has done that for us. So, but I'll just write it all, 1299.6 plus negative 787 plus a negative 285.8. That should be a 0. I'll explain that in just a second. And that's going to equal positive 226.8 kilojoules. Exciting. Okay, so why did 5/2 cancel out? So 5/2 is the same thing as saying 2.5, right? Here we have 2 oxygen. Here we have 0.5 oxygen. And since we're adding all the reactants together, 2 oxygen plus half an oxygen is 2.5 oxygens, and that's why it's going to cancel out. So does that answer that? That's why those guys cancel. Okay, so the only thing that you guys are going to be worrying about here is just making sure your reactions are in the right directions and that you have the right coefficients. And that's it. That's all you have to do. Add them up, and poof, we got our answer. Is this reaction exo or endothermic? Yes, this is endothermic, yep. So it would cost us energy to make this acetylene, which is why when we burn the acetylene, it gives us back energy. Exciting stuff. Very nice. Do we have questions on that one? We are going to do another example. Correct. Yeah. The surroundings would have to put in some energy, so they would lose some energy. Absolutely. And so let's just double check, by the way. We're looking at C2H2. We have here 226.7, it looks like. Is that what we got? Yeah, we got 226.8, so looks good. So another way, just double checking. So they probably just have slightly different numbers for their things, but lo and behold, we were able to check it. Cool. Other questions on that one before we do another example? Okay, I'm not seeing any, so let's go ahead. So this reaction we're going to do now is carbon plus water. I think that's liquid. No, it's gas water. Okay. Okay. And we're going to be given 3 reactions. We're given carbon plus oxygen turns into carbon monoxide, or carbon dioxide rather. And delta H for that is negative 390. I swear we've done this reaction every single time. We have 2 carbon monoxides. Plus oxygen. Going to, and so the idea here is you would be given these 3 reactions, right? You're not going to have to come up with them yourselves. Negative 556 kilojoules. And then the last one, turns into water. 2 waters. Yes. Okay. This is example. I guess this is practice exercise 1 or something, whatever. We can do it. So, with that, let's go ahead and look at these reactions. Do we need to do anything to the first reaction? I don't see anything that we need to do. We have carbon solid as a reactant. We're looking for carbon solid as a reactant, so I would suggest we leave this alone. What about the second reaction? What about water being a liquid? No, definitely not Star-Lord. Absolutely not. In this case, these 3 reactions are given to you as they are. So water is a gas in this reaction. We're going to accept it like that. We're going to see when we talk about enthalpies of formation, that's when water has to be a liquid. Okay, so I would agree we are going to reverse this and also divide by 2. So because we want carbon monoxide as a product, but we only need one of them. And this reaction has two of them. So we're going to have to divide this reaction by 2. And if we look at the next one, it's going to be the same thing. We're going to have to reverse it and divide by 2. So first reaction we're going to leave alone. Second reaction, we're reversing and dividing by 2. So delta H doesn't change for the first one. For the second one, we're making it CO2 turns into CO. I guess I should put gas for these, plus half O2. So again, that's why we're going to see these fractions around, just because typically that's going to make it easier for us to look at individual other ones. So delta H for this one is going to be we have to make it reverse the sign as well as divide by 2. Someone do that for me. In the meantime, I will flip our other reaction around. Same thing here. We're going to have to 483.6 divided by 2. God, this is so messy. Oh, I hate how much writing is here. We'll make these nice. This is 278, you said? And how about that last one? If someone would not mind. And while they're calculating the delta H for that one, let's go ahead and look at this reaction. Let's make sure everything we don't want cancels out. So when we add these, we want to get carbon plus water turns into carbon monoxide plus, what was it, hydrogen? I don't remember. Yeah, hydrogen. So let's see. We don't have O2. Okay. Shane's number looks reasonable. I'll just go ahead and put that. 241.8 kilojoules. Okay. So looking at these, we have oxygen here that we need to get rid of. And that's going to be these two guys. Half oxygen plus half oxygen is a whole oxygen. Those can cancel out. We also do not want carbon dioxide. So that guy will cancel out as well. And doing that, it looks like everything else is okay. We have 1 carbon, 1 water, turning into these two guys, 1 of each. And so now we can go ahead and add up our delta H's. Negative 393.5 plus 278 plus 241.8. I think this should be 0.0, but whatever. That'll be okay. Doing these, 278, 241, minus 393.5. So doing this, I got 126.3 kilojoules. And so that's our reaction energy. Yeah, and this will also be endothermic. For sure. Technically, yes. Kilojoules for a reaction should be per mole. Yes. And that's typically the moles of the product. Alrighty. I know we are out of time, but I want to give you... Now that's going to take too long. Okay. Okay, then I guess we'll do that on Monday. Okay, so with that, hopefully this stuff is not too bad, I hope. It's just flipping reactions around, making things positive, making things negative, whatever, and adding them up. So this stuff is, I think, a little bit easier. Next time, we're going to talk about, yes, it is a lot of work, but it's simple algebra, essentially. But a lot of work. Yes, I agree. So with this, let's find out. Where is the homework here? I think you'll be able to go up to 66. So you'll be able to go through 66, and then the rest of them are going to be using heats of formation, and that's stuff we're going to talk about on Monday. Okay? So you will totally be able to get through 66 with all the fun stuff we've done so far. Okay. Any questions? Do you have homework due on Sunday? Do you have anything due this week? Maybe solution stuff? I don't even remember when we did that. Let's check. Yeah, you do have your molarity homework is due on Sunday, but that's like 2 pages or something. It's easy. So that one you should be able to do, and then this stuff will be due the following Sunday. So you'll be able to do at least 75% of your thermochem homework if you want, but again, yeah, you will not be able to do quite all of it yet. Alrighty, so with that, have a nice weekend. Hopefully this made a little bit more sense than some of the other calorimetry stuff that we've talked about so far. But again, it'll get easier the more you do it. So that's why I gave you so much homework. It's not because I love grading. Obviously, it's quite the opposite, right? I hate grading, but it's for you. All the sacrifices I make. Yeah, right. Okay. See you guys. Take care. As always, throw questions in Discord if you have them. Otherwise, have a great weekend. And yeah, take care.